One important methodology in product design is the application of decision trees through product design. It's particularly very useful when there is a series of decisions and outcomes that lead to other decisions and outcomes, and I would like to find the optimal decision if I have several options. Then for that there is a methodology, and the procedure basically is to include all possible alternatives or state of nature, including the option of doing nothing. Maybe I am not going to develop the product because I decide not to do that. Enter the payoff at the end of the branch. The payoff is the profits or loss of designing and developing a product, for instance, and determine the expected value of the branch and prune the tree to find the alternative with the best expected value. Let's try to explain this with an example. Silicon, a semiconductor manufacturer, is investigating the possibility of producing and marketing a microprocessor. Undertaking this project will require either purchasing a sophisticated CAD system or hiring and training several additional engineers. The market for the product could be either favorable or unfavorable. Silicon, of course, has the option of not developing the new product at all. With a favorable market or a favorable acceptance, sales will be 25,000 processors selling for $100 each. But with an unfavorable acceptance, sales just be 8,000 units selling for $100 each. The cost of the CAD equipment is $500,000, but that of hiring and training 3 new engineers is $375,000. Manufacturing costs should drop from $50 when manufacturing without CAD to $40 each when manufacturing with CAD, because of course you use a computerized system, the manufacturing costs are going to decrease. The probability of a favorable acceptance for the new microprocessor is 40%. There is a favorable market, is 40%. The probability of an unfavorable acceptance is 60%. There is more probability that the market is not going to accept the product. Now, what is the best decision for Silicon Inc? We have here 3 alternatives. One is to buy the CAD equipment that have a cost and however is more productive and efficient, but is costly. The other is to train the engineers for doing this process, the design of the product by themselves without the using of the CAD equipment. And the third decision is doing nothing. Then we are going to represent in a decision tree all the alternatives. One is purchase a CAD system, the other is hire and train the engineers, and the other is doing nothing. Now, if we purchase the CAD equipment, we can have favorable sales with a probability of 40% and low sales with probability of 60%. The same if we hire and train engineers. Of course, we are doing nothing. We are not going to consider that. Now, if we purchase the CAD equipment and has high sales, the revenue is going to be $2,500,000. Why? Remember that we can sell 25,000 units at a price of $100 each. If we multiply 25,000 by 100, the revenue is going to be $2,500,000. Now the costs are going to be the $1 million, the manufacturing cost, because the unit cost is $40 and we are going to produce 25,000 units. Then the manufacturing cost is going to be $1 million. And the cost of buying the CAD equipment is $500,000. Then we subtract the cost from the revenue, and the profit is going to be $1 million. With low sales, the revenue is going to be less because we are just going to sell 8,000 units. Multiplied by $100 is just $800,000. The manufacturing cost is going to be $40 because we are using the CAD system, at $8,000 is $320,000, and the CAD, the equipment, it costs $500,000. Then we have a net loss, a negative profit or loss of $20,000 with low sales. Now, if we hire and train engineers, then the costs are going to be with high sales, the revenue still is $2,500,000. The manufacturing cost is greater because now the unit cost is $50 per unit, multiplied by $25,000 is $1,250,000. And the additional cost is to hire and train the engineers. The cost is $375,000. Then the profit is going to be $875,000. And with probability of 60%, with low sales, the revenue is going to be $800,000 because we just are going to sell 8,000 units. The manufacturing cost is going to be $400,000, and the hire and training engineers is $375,000. Then we have a profit of just $25,000. And doing nothing is $0. We are not going to have a profit or loss. Then we have here that we have $1 million with probability of 40% and minus $20,000 with probability of 60%. Then what we do is multiply this value, the net payoff, times the probability that's going to happen with 40%. 40% of 1 million is $400,000. And then minus 20,000 multiplied by 60% is minus $12,000. Then if we subtract 400,000 minus $12,000, it's going to be 388,000. We do the same, then that calculation is here. 0.4 times 1 million plus 0.6 times minus 20,000. We do the same for low sales. For the engineers. Then the purchase of the CAD, the expected value is 388,000. For training engineer, we multiply 875,000 times 40% or 0.4 plus 25,000 times 0.6 is going to be $365,000. Then between the three results, we eliminate this and this because are lower. The profit, we maximize the profits if we purchase the CAD equipment. Then the decision here is, in order to design this product, we are going to purchase the CAD equipment, and we are not going to hire and train engineers because it's easier for us to purchase the CAD equipment. This is the explanation of the decision tree.